Hi everyone, so my name is Krili D'Souza and this is going to be part 1 of 3 of me explaining an FRQ from one of the past AP tests. So the first one that we're going to be doing this video is the 2015 AP Physics free response question number 4. This is the first page, but to start off, hi, Mr. Bravico. I'm going to read out the problem and we'll go from there. We'll study the diagram because there's a nice little diagram given to us and we'll go from there. So, 2 identical spheres are released from a device at time t equals 0 from the same height h as shown above. So we can see the 2 identical spheres and h is the same for when they're released. Sphere A has no initial velocity and falls straight down. We can see its trajectory straight down. Sphere B is given an initial velocity of magnitude v0 and travels a horizontal distance d before it reaches the ground. So, sphere B, right there, I drew in an arrow that shows v0, the horizontal constant velocity that it's given, and it travels a distance d, horizontal distance, before it reaches the ground. The spheres reach the ground at the same time, TF, so they reach the ground at the same time. It's not really part of the diagram, even though sphere B has more distance to cover before landing. Assume that air resistance is negligible. So, 4A asks, the dots below represent spheres A and B, these 2 dots. So we're going to be drawing dot diagrams. Draw a free body diagram showing and labeling the forces, not the components, exerted on each sphere at time TF divided by 2. So, sorry, I had to cut the video due to some background noises by the rest of my family and some distractions, but I'm back. So we just finished going over part A of the problem. And so free body diagrams are drawn to represent the forces on a certain object or system, and there's many different forces that could be acting upon an object. A couple of examples is normal force, force of gravity, force of friction, those are force of tension. However, in this scenario, we'll go through each of those and show why there isn't those forces acting upon it. But first, let's talk about time t final divided by 2. So that means we know it's not going to be at the initial time or at the final time. It's going to be halfway in between, and the objects will be falling through the air, right? Because the time it takes for it to travel here, time it takes for it to travel here, somewhere in between. And that's really important because that means that there will not be normal force acting upon these spheres because they don't have a surface that they're on. And normal force is defined by a force that is perpendicular, goes perpendicular to, or the magnitude is perpendicular to the surface of, to the surface of an object. So, or to the surface that the object is on. So like if this is the object, if that is the object, the normal force is going upwards and force of gravity would be going downwards. So like my water bottle on my table right here, there's a certain force of gravity that's pulling it down, which is mg, and there's a normal force that the surface, the table, is exerting up on the water bottle. And that is what's keeping it from moving in the vertical direction, up or down. If we think about like in space, how there's kind of a different force of gravity, no force of gravity, things move around, and that's my comparison. Okay, so there's no normal force, right? Because it's in free fall, no surface to have the normal force on. There's also no forces of friction because again, there's no surface that it's moving on. And friction is the coefficient of friction times normal force. And if normal force is 0, no force of friction. And then force of tension, there's no tension because there's no strings, there's nothing holding it up. So all that leaves us with is force of gravity. And so that is what I have drawn here for both of these spheres because they both are experiencing the force of gravity. Now, what is the force of gravity? So it's a force that's pulling these objects towards the surface of the Earth. Now, in this scenario, we can assume that the surface of the Earth is, over there. But if you think about this on a planetary level, if the spheres were satellites and the planet was Earth somewhere else, the arrow force of gravity could be pointing elsewhere. So we have to assume that this is on the surface of the Earth, and that that's the way that it's being pulled is downwards, which is towards the surface of the Earth. And force of gravity can be defined as mass times the acceleration due to gravity, which is 9.8 meters per second squared. We don't really need to get into that because if you remember, the question said labeling the forces, not the components. So it's best to write it as force of gravity, which I've done. And as you can see, the arrows are equivalent in magnitude because since they're identical spheres, we can assume that their masses are the same. And since force of gravity equals mg, that means the mass times the acceleration due to gravity, it'll be the same for both of them, so same magnitude. So that is this first part. We can move on to the next question, part B. I think that's part B, yeah. So it says, on the axes below, sketch and label a graph of the horizontal component of the velocity of sphere A and of sphere B as a function of time. So actually, let's just think about that for a second. If we go back to our initial diagram, the description told us that sphere B is given an initial horizontal velocity of a magnitude v naught. So it asked us to draw the horizontal component of the velocity. So sphere B has a vertical component of 0. However, it does have that initial velocity, and that velocity, that horizontal velocity, is going to be constant because it's not affected by vertical velocity or vertical acceleration or anything like that. So that is going to stay constant throughout the journey or the trajectory of sphere B. So I drew it as this straight line here, showing that velocity is constant, the horizontal velocity, and I labeled it as v naught because we aren't given an actual value of it. So that is what we would label it as because that's what the information we were given in the initial description. Now onto sphere A. Here we can see I did not draw a vertical or a horizontal component of velocity for sphere A because in the description it says sphere A has no initial velocity and falls straight down. So not only does it have a vertical velocity of 0, it also has a horizontal velocity of 0, meaning that the whole time the horizontal component of velocity is going to be 0 until t final. So why this ends halfway or at this point through the graph, I actually labeled this as time final because it could have gone all the way through and I could have said time final was there or here, but this time final point is to represent that the constant velocity of sphere B ends at time final because, yeah. So that is part B. I'm not sure if there's anything else to really cover with initial velocity. I could talk about the force exerted on it, if that's helpful. I think a common question that I used to have about this diagram or just this scenario is why are there no forces in the x direction acting on sphere B, right? Because if there's a horizontal velocity and that's, causing it to go travel distance d, then why isn't that considered a force? And so the reason for that is because the forces in the x direction is 0 because the acceleration in the x direction is also 0. Because as I said before, that v naught is constant, meaning that there's no change in velocity. If there were a change in velocity, that would constitute as an acceleration greater than 0. And going back to Newton's second law, not sure if you know this one, I'll go over it really quickly. The law constitutes that forces equals mass times acceleration, is the product of mass times acceleration. It's one of the basic laws, and it's really helpful in this physics problem to think about, conceptualize what's going on and why velocity isn't a force acting on it, even in the horizontal direction. So if we think about it like the sum of the forces in the x direction is acceleration times mass, right? We know that mass is not 0, so mass is not 0. This is just what I'm writing over here. However, we also know that acceleration is 0 because the velocity is constant, no change in velocity. So that determines that the forces in the x direction on this sphere B is also going to be 0 because anything times 0 is 0, right? We know that. So sum of forces in the x direction equals 0. So that can also be, that's also an important thing to note about why I didn't have a horizontal arrow saying that velocity was a force, because it's not a force and there are no forces acting in the horizontal direction, as I just proved over here. So, yes. I mean, while we're talking about Newton's second law, we could also talk about Newton's first law, which has to do with this as well. It's that objects in rest stay in rest unless acted on by an external force, and objects in motion stay in motion unless acted on by an external force. So we know that these objects were released from rest. So we can assume that they were standing on a surface, the balls were laying on a surface, and the surface got pulled out from underneath them. Okay, so once again, I needed to cut the video because turns out my phone does not have enough storage to film these. Also, yeah, background noises again, just to preface, but let's get back to what we're talking about. I'm pretty sure that I explained Newton's second law and I was going on to his first. So, the first law states that objects in motion stay in motion unless acted on by an external force, and consequently, objects at rest stay at rest unless acted on by an external force. So let's take our example over here, right? So it says that they are released from rest. It doesn't really give specifics to how that happens. So we could say that the two balls were being held in my two hands, right? And with one of them, I just let it go and it dropped. That was sphere A because there was no initial horizontal velocity, just dropped. However, sphere B, I threw it perfectly horizontally to the side with an initial velocity v0. And I watched them drop, right? So at this point, there was me holding them up, of course, and the force of gravity, but those two forces were equivalent while I was holding them while they were at rest because they weren't moving in the vertical direction. However, when I let them go, all that was acting upon them in the vertical direction was the force of gravity, and that caused them to accelerate downwards and hit the ground. So that kind of relates to Newton's first law in the sense that they stayed at rest until acted on by that external force, which was me letting them go and throwing one to the side. And it was the external force that happened was the removal of the force of me holding them up. So that is how it relates to Newton's first law. I think maybe we could do a review of Newton's second law again, F equals ma, and we can talk about it in terms of sphere A and sphere B because it is really helpful to explain why these forces aren't, why there aren't other forces acting upon it. And, I guess actually, let's go to part C because that kind of involves what I'm talking about. So what the question is in a clear, coherent paragraph length response, explain why the spheres reach the ground at the same time, even though they travel different distances. Include references to your answer to part A and B. So let's think about that. It's a little bit counterintuitive because when we look at this diagram, right, we see, well, B had to travel all this distance, whereas A only had to travel that much, right? And it's kind of like, you would think that B might take a longer time to hit the ground because it just had that longer trajectory, and that's kind of what makes sense in your head. Well, I definitely thought that at some point too, but here's the reason why that's not the case. And it kind of relates back to what I've been talking about in the rest of the video. So actually, maybe I can read out my paragraph response and then we can talk about what I was saying. So, the only force acting upon both of the spheres is the force of gravity, which pulls them towards the Earth. In this case, that's downwards, which again is why I had these two arrows showing the force of gravity equivalent in its magnitude, pointing them downwards. And we talked about why velocity, the horizontal velocity, is not a force that's acting upon either of the spheres. Well, more specifically sphere B, because that's the one that has an initial velocity. Anyways, like I said, although sphere B has a constant horizontal velocity, there's no acceleration in the horizontal direction, which means that there are no forces in the horizontal direction. And sphere A does not have any velocity in the horizontal direction. Both of them having, whether or not they have velocities in the horizontal direction, it does not matter because this does not affect the time that it takes for both of the spheres to travel. In sphere B's case, it does affect its path, but only in the horizontal axis direction. So basically, the initial velocity that B has in the horizontal direction is going to have a relationship to the distance that it travels horizontally, but they're falling from the same height, sphere A and sphere B, and they both don't have any initial velocity or no vertical component of an initial velocity. And because of that, the acceleration is just the acceleration due to gravity, and which is an equivalent force that is acting on both of the spheres, which means that they will both be accelerating at 9.8 meters per second squared towards the ground. And I think a really key part of that explanation is remembering that horizontal acceleration, horizontal velocity does not affect vertical velocity or vertical acceleration. And although that might seem difficult to separate them, we actually do that quite a bit in physics, taking the components of gravity, the components of tension, the components of just velocity. There's a lot of taking the vertical component and horizontal component and separating them in your head. So it's really key to remember that horizontal acceleration doesn't affect vertical acceleration. I think that a key to understanding this problem and how to do it is actually understanding what free body diagrams are and what they consist of and how to draw them for different objects, different systems. So I think that we should do a couple of other example free body diagrams to just get that concept. So bringing back my water bottle, let's draw a free body diagram for this water bottle and it's going to be sitting on this table. So I'm just going to draw a block for the mass, and we know that it has normal force, and we know that it has a force of gravity, and that would be a free body diagram for this water bottle when it's at rest. Now, let's say I start moving the water bottle this way with my hand, right? So then it has an applied force, and let's say I'm just pushing it straight on, so in the perfect horizontal direction. That is going to have a different free body diagram because now there are new forces acting upon this water bottle, right? Because it's moving. So there's got to be a new free body diagram. So we're still going to keep our normal force and our force of gravity, and those are going to be equivalent in magnitude to each other. You might be thinking, how can an object at rest and an object at motion have the same forces still acting upon it? And it goes back to the concept what we were talking about, where the vertical components do not affect the horizontal components. So some horizontal components that we'd have is the force of friction as well as the force applied. So we're going to say that I was pushing it this way to the left, right? So actually, as a matter of fact, these arrows that I drew are going to be pointed in different directions. So I'm pushing it this way, and someone's like, show me how to draw a free body diagram for that, right? And this is what I would show you. And I know it looks complicated at first glance, but it's quite simple. So the normal force and the force of gravity are equal because it's not moving up or down, not moving. And the force applied is in this direction because I'm pushing it that way. And the force of friction is in the other direction, acting this way, opposite the direction that I'm pushing it. And friction, as I think I mentioned before, is mu, or the coefficient of static friction, or in this case, since I'm pushing it and it's moving, it would be the coefficient of kinetic friction times the normal force. And that is a force that is kind of pushing against the way that I'm trying to move it. So it's in the opposite direction. So the net force in the horizontal direction would be, F applied minus force of friction. Now you might be thinking, why is it not the other way around? Why is it not force of friction minus force applied? Well, that's because we know that in overall, it is moving in this direction, the direction that the force applied is being exerted. So we know that overall, the net force is going to be in that direction. So the force of friction is just something that's acting against it. However, it's not stopping it. It's not bringing to a halt. But say that the friction was equivalent to the force applied. So say I only pushed this much, right? You can see that it's not moving. And that's because there's the force of friction pushing back on the way that I'm applying it, you know? I'm pushing, it's not moving because the force of friction is strong enough to be equivalent to the force applied. So I think that's a really essential part of thinking about horizontal and vertical components and why objects move in the way that they do, and the directions of vertical components and horizontal components, and which you need to factor in. The answer is you should factor all of your horizontal components into when you're drawing free body diagrams, but you should not split it up into like specific components. Remember how I was explaining that sometimes in problems you need to split them up into components. So I think I haven't really showed an example of where that would make sense to split it up. So I will show you one right now. So say there's a box that is on an inclined plane, right? On a slope. It's standing still on the slope, right? So what are the forces that are going to be acting on this box? Let's think about it. So the free body diagram that I drew right here has normal force, which is, you might think that it would be opposite of gravity. However, normal force is perpendicular to the surface that the object is resting on, not opposite to force of gravity always. So on this inclined plane, it would actually not be opposite. As we can see, this arrow is not opposite that arrow. If it was, it would be pointing straight upwards, right? But the force of gravity is always going to be pointed towards the center of the earth, the surface of the earth. So that's going straight down. It's not, again, it's not perpendicular to the surface of that the box is resting on. So here we would want to split this up into the horizontal and the horizontal and vertical components of, let me draw this bigger actually. So this was the arrow that I had drawn initially because that's pointing towards the surface of the earth, but I can split it up into horizontal and vertical, or vertical and horizontal components. I like to label it as FGY and FGX because that helps me remember x-axis, y-axis. It's just a helpful trick. And those can be used in terms of being opposite in horizontal direction of this surface and the perpendicular direction to this surface, because now the vertical component of the forces of gravity is opposite the normal force. And if there was friction here pointing the other direction, if it was trying to, let's say it's trying to move downwards, it's moving downwards, friction is going to be pointing upwards, the opposite direction that it's moving. And FGX, the horizontal component of gravity, is going to be pointing in the other direction. And so those would be opposite to each other. And generally, it just makes these problems a lot easier to solve when you think about it like that in components. However, it is really important to remember that in free body diagrams, it's never asking you to split it up into those components yet. So, for example, if there's a planet and a satellite, like the Earth, and there's a satellite orbiting it, you're just going to want to show, and it asks you for a free body diagram of the satellite and what forces are acting upon it. You just want to show that force of gravity. Say, oh, that's a horrible drawing. Say that's the Earth and that's the satellite. You just want to show the force of gravity going towards the Earth, no matter what the problem is on the free body diagram. Later on, you can split it into components and do that, but on free response questions, it's important to be careful of mistakes like that. Okay, so now we're going to go back through this problem and review all the concepts that are necessary to understanding it, and just go through it one more time to make sure we got it. Let me erase all of the extra stuff that I drew on there, free body diagrams and whatnot. While I'm doing that, we can just talk about how essential free body diagrams are to physics, because I've learned that any equations that you really making a free body diagram helps so much to understanding them. And thinking about forces and all of that is a lot easier when you know what goes on a free body diagram and what doesn't. All right, so back with our two lovely spheres. Sorry about the background noise. And let's just review Newton's laws and why they're important to this problem. I think the one that's most important is the second law, which is that force is mass times acceleration, the product of mass and acceleration. And we drew this little free body diagram showing that force of gravity is pointing downwards and that they're equal in magnitude. And we did not draw any arrows for sphere B or for sphere A in the horizontal direction. And that is because although there is V0 for B, that V0 is constant, and it's going to be constant throughout its whole period of travel time, as we can see here. So you might be thinking, well, that sounds like an applied force to me. That sounds like something that's being continuously applied, that's keeping the ball in motion. Why isn't that a force that is on your free body diagram? And the answer to that is that when we think about forces, we think F equals ma, right? And the velocity is constant, which means that the change in velocity is constant. And change in velocity is what acceleration is. Velocity over time. Velocity over time, yeah, the derivative of velocity. It helps me to think of it in calculus terms, but I'm sure since you guys are middle schoolers that that's probably not helpful. But so when acceleration is 0, if we go back and we remember that mass times acceleration is force, and no matter what the mass is, the mass could be 1, the mass could be 100, the mass could be 1,000, acceleration is 0, and anything times 0 is 0. So we know that the sum of forces in the x direction is m times 0, so the sum of forces in the x direction. Another essential part to understanding this is knowing all the forces that could be written on this free body diagram and why they aren't. So like we said, let's go back to the different ones that could be there. So there's normal force, there is the force of friction, and there is the force of tension. And I'm going to be talking about some of those in later problems. As you can imagine, tension really comes into play when there's a string or something holding something else up. So like if there's a ceiling and there's a string and there's a mass attached to that string, then there is, well, let's think about that actually. What would a free body diagram look like for something that's hanging from a string from the top of the wall? Well, it would be force of tension and force of gravity, right? And they are pointing in opposite directions of each other, assuming that this is on Earth again. Most of the scenarios that I've created have been where we assume that it's on Earth and the acceleration due to gravity is 9.8 meters per second squared, and that downwards is towards the surface of the Earth. But so that's one scenario where we could see force of tension. A scenario where we'd see force of friction is well, there's really anything. Just a box lying on the table, force of friction, and or let's say it's moving this way, force of friction is going to be pointing in the opposite direction, and the force applied is the next one. Force applied, force of friction, opposite directions because it's acting against the way that it's moving. And when you don't apply enough force, it doesn't move because the force of friction is preventing it from moving. That in that case, the force of friction is greater than the force applied. Yeah, so those are some of the forces, and those are some of the past scenarios that I've explained are some scenarios where these forces would be put on free body diagrams. However, our spheres at t final divided by 2 are in free fall. They're in the air. There is no surface that they're on, so no friction, no normal force, and there's no string holding them up. So like I said, the only force that's going to be acting on them is the force of gravity. Something else that I think is important to note is that the problem states that air resistance is negligible. So when we're thinking about that, there's something falling, right? And what is air resistance going to do? It is going to slow it down, right? Air resistance means that it's not free falling perfectly through the air, and that there's some force of resistance towards our downwards acceleration. So if air resistance was not negligible, our free body diagram would look a little different. Let me draw what it would be for sphere B and sphere A. And let's assume that the air resistance is not preventing it from falling completely. It's only slowing it down a little bit. So the new free body diagrams would look a little something like this. And you might be thinking, why is the arrow of air resistance smaller in magnitude than the arrow of force of gravity? I don't know if that's, I probably could have made that a little bit more distinct, but like I said, in my made up scenario, the force, it's still falling downwards, which means that the net force is downwards and the object is still able to move downwards, which means that air resistance is doing something to slow it down, but it's not stopping it completely. And that's kind of similar if we think about what I was talking about with friction and applied force, where if the object is not moving, then the force of friction is greater than the force that's being applied. But if the object is moving, then the force of friction is less than the force being applied. And that's kind of similar to this air resistance dilemma. However, negligible means that we don't really have to consider it in this problem, which makes it a lot easier. So we can we know that in a real life scenario it would exist, but we can kind of ignore it for the purposes of this problem. All right. I think the next thing that would be important to review is the difference between the horizontal and the vertical components of velocity, of force, of gravity, of anything really, but in this specific problem, it's relative to velocity. It's a really key part of physics to remember that the horizontal components of things don't affect the vertical components. And in this problem especially, it's key to solving part B and drawing a correct graph, because if we think about it, a vertical, you might be thinking, how can we prove that the vertical component and the horizontal component are separate? Well, for sphere B, it says it has an initial horizontal, which is this way, x-axis, velocity of v naught, but it does not specify that, or it's just given that initial horizontal velocity. However, and so that's why we drew a constant horizontal velocity for sphere B. However, if this graph it told us to draw the vertical component of velocity, then where do we think that these lines would be for sphere A and sphere B? I don't know, I asked you that question, you can't respond. The answer is that they would both be at horizontal or at vertical velocity 0, because neither of them have an initial vertical velocity. Yes. And that would have to be the initial vertical velocity, because there is acceleration due to gravity, but since they're released from rest, we can assume that their initial velocity is 0 for the both of them in the vertical direction. I need to specify that because we learned that, or the description states that in the horizontal direction, sphere B does have an initial velocity of v naught. I think that's kind of all for those first two parts of the problem. I'm going to read through my paragraph one more time and kind of break down each point of what I was saying. So, the only force acting upon both of the spheres is the force of gravity, which pulls them towards the Earth. And in this case, that would be the downwards direction. In a planetary or in space, this might be different. It's not always downwards. We're assuming that this problem is talking about being on the face of the Earth. Although sphere B has a constant horizontal velocity and sphere A does not, this does not affect the time it takes for sphere B or A to fall but only the horizontal distance that it travels. So we know sphere A has an initial horizontal velocity of 0, which is why it does not travel any horizontal distance. It only drops a certain height. So the fact that both of their initial vertical velocities are 0 does affect that, in the sense that they both travel at the same time with the same acceleration due to gravity downwards, and they hit the ground at the same time because their initial velocity in the vertical direction is the same and their acceleration is the same. And we can kind of infer that by thinking of these equations. We know that the time it takes has a direct relationship to the initial velocity and the acceleration. And so I want to refer to an equation off of our handy dandy equation sheet. You do not need to know all of these. You guys are in middle school, so I'm sure that that's not as valuable to you as it is to me. But we refer to these equations in kinematics a lot to kind of determine the relationship between initial velocity, time, acceleration, and often there's 3 different versions of these equations, and often we'll be given two or 3 components and asked to solve for the 4th. So I picked the equation V final equals V naught, so V initial plus acceleration times time, right? And so just to go over what each of those mean, V final is the final velocity, so the velocity right in this case it would be the velocity right before the object hits the ground. V naught is the initial velocity, A is the acceleration, and T is time. And so I just did a little bit of algebra to solve for T. And how we get to that equation, I'll read the equation out. It's T equals V final minus V initial divided by A. And the process to do that would be subtract V initial from both sides, right? So then we get V final minus V initial equals AT. There, if you need a visual to help you see that. And then we divide both sides by A because we're trying to get T all on its lonesome. And that would give us our equation, which is, let me repeat it, T equals V final minus V initial divided by acceleration. So we can manipulate these equations kind of however we want to, which is what I did to fit our situation. And now I'm going to specify that I'm talking about V initial, V final acceleration in the Y direction, in the vertical direction, which is a very important part because V initial is not the same for sphere A and sphere B if we were talking about the horizontal component. So I have to specify that it's in the Y direction. So I'm just going to add Y's to my V final and V naught. So now it's V final in the Y direction minus V naught in the Y direction divided by A equals T. So now let's bring this back to our spheres, right? We know that they have the same initial velocity of 0. We know additionally that they have the same acceleration, which is the acceleration due to gravity. And since the initial velocity is 0, we know their acceleration, we know their final velocity will be the same as well, which means that their time is going to be the same. And that proves kind of what the problem C, part C, was asking, which is that explain why the spheres reach the ground at the same time, even though they travel different distances. The key to understanding that is that the distance in the Y direction, in the vertical direction, is the same. However, the distance in the X direction that they travel is different, but that has no relation to the time it takes them to fall from their initial height H. I think that pretty much covers it. I think it's important to remember Newton's laws, especially the first and second for this problem. So I'll reiterate, the second law is force equals mass times acceleration, F equals ma, and that can be split into y components and x components, as many other things can. And the first law is that objects in motion tend to stay in motion unless acted on by an external force, as well as objects at rest tend to stay at rest unless acted on by an external force. And those are really the key concepts it takes to understand these problems and get through them and get full credit on them. So I hope you guys have enjoyed watching my videos, just my one video, and I hope that this explanation was helpful. And I'm not sure if you're seeing this, Mr. Babago, but that's all.